This is lecture 7 for chapter 5 of Calculus 3, and in this lecture I will show the procedure and the derivation for line integrals of vector functions. Remember, in the previous lecture it was the line integrals for scalar functions. So when we're talking about line integrals of vector fields, we're talking about the integration of a vector field along a path. Remember, it doesn't have to be a straight line, and this could in fact be the curve, like the circle around a disk. But as before, the vector field can be broken into two components. One component is going right along that path, the other is a component perpendicular to it. And this is just a refresher from a previous lecture. When we integrate that tangential component, that's a component going right along the path that gives flow along the path, and it could give work. If it's closed, it can give circulation. When we integrate the normal component, we get flux. The following is a sketch that I attempted to make, which shows why in these lectures I borrow diagrams from other people on the internet, especially if you knew how long it took me to do it. That's the real pitiful part. At any rate, what we're talking about here is integrating along this line, in this case this circle. So this is going to be the line we're going to go around. We're going to have, it's going to be parametrized, and we're going to go around this line. Okay, like say, of course, oval or circle. Here is the vector field F we're going to integrate. Now, the component that's perpendicular, which hardly looks perpendicular here, this perpendicular component, or normal component, if we integrate that, we get the flux. When we integrate the tangential component, remember that tangential component is going to be different at every point here because it's tangent to the curve. Okay, we'll integrate this parallel or tangential component. Then we get circulation if it's closed, or flow if it's a fluid, or it could be work if F is a force field. So scalar, you didn't have to worry about it. For a vector, you do have to worry about this. Two components. And here are the equations. So I'm showing you the equations up front, and then I'm going to show you how the derivation and how to use them. If you mastered what was done for the scalar, it's pretty easy to go to this point. Okay, if you want the tangential component, you remember R is a parameterization of the path. Okay, here's what this is: integrating the tangential component, giving you flow, circulation, and work along a path parameterized by R of t. It looks a lot like expression for work in the past, right? Anyway, here is the corresponding expression for the scalar field. It looks very similar. You take the vector field, you compose it with the parameter R. Here you took the scalar field. Okay, I've got the pin now. Okay, this is the vector field composed with the parameterization R. Here was the scalar field composed with the parameterization R. This is a vector. This was still a scalar. It was a scalar field. It remains a scalar after it's been parameterized. Now, the next term here is the time derivative of the parameterization. Remember, R dot is dr by dt. Okay. For scalars, you simply multiply, but in this case by the magnitude of R dot. The reason this is multiplication is because these are both scalars. Here, well, this is a scalar because you've taken the magnitude. Here, you still have a vector. R dot is a vector. And now the operation is dot product. See that difference? Also, what really happened to the magnitude of R dot? And I'll show you that in the derivation. This is for integrating right along the path. So you run along the path and you want to integrate that function right along the path. So it's a vector function. Let me get a better color than that. Green. So you want to have the tangential component just project as though it's projected right along that path, and that's your parallel or tangential component. Okay, the dot product does that because it projects it down onto our dot. Right, and you're getting flow, circulation, and work from that. Now when you're integrating the normal component, you want flux. How do you get the normal component? You do the same thing, F composed with R. That puts your vector field right on the line, and as t changes, you just pick off the value of the vector field along that line. Now you dot it with the normal. Okay, so that makes sense. The dot with the normal, so here's your line, and here's the normal to the surface. When you take the dot product of F, say F looks like this with the normal, you're going to get the normal component. This is pretty much a repeat of what we just said. We're going to parameterize the line or the path along which we're going to take the line integral. Here's this parameterization. We assume it's continuous with a non-zero continuous first derivative r dot. We assume the path is simple, and well, let's go ahead and assume it's closed, and it has a positive orientation. That means I'm going to be able to assign these normal vectors to it. This is the vector field as we've written it this entire chapter. Capital F, boldface, in terms of x, y, z. In this case, we're only going to do Cartesian coordinates, and the components are m, n, and p. Now the way to look at this is that while a scalar function, all you did was project it onto the path through composition. Projected was a bad word. You compose it with a path in order to just pick up the function, the values of the function along the path as t changes. Okay, so you just use composition. For the vector fields, let's think of it as though there are two steps required. I like to think of it this way. The first step, you go ahead and do that composition just like you did before. So you end up with, that's kind of poor notation. What you end up with is, let me find the pin here. You end up with F composed with R. That will be, M is now varying with T in the I direction, N varying with T in the J direction, and of course P varying with T in the K direction. So let me write that up here so it looks a little bit better. So F composed with R is going to give me M varying with T. It's unnecessary to have written that, but not wrong what I wrote before. N varying with T in the J direction, and P varying with T in the K direction, because we want it in terms of the parameter. So if the path is this is an elliptical helix. You see, it would be a circular helix if it was a 5 in front of here, or if they both were 1s. Okay, so you have this elliptical helix, and here we have a vector field, x, y, and the I, plus 3x squared j, plus 5 z squared, and there should have been k on the end of that. That looks like it got left off. Okay, so to parameterize it, every place there's a z, I put a t, so that's why that came in right here. Every place there's an x, I put cosine t, and every place there's a y, I put 5 sine t. So here's my 5 sine t, and this is 3 times y squared. Ooh, that shouldn't be 15. That should be a bigger number. Okay. So, well, at any rate, that's an arithmetic mistake. I composed, but the end result is I composed F with R, and I end up with a new function, well, that is a vector field in terms of time. So that first step is common both to flux and to circulation or work. So just first step is just to compose it with the function, with the parameterization. Here's how we do the tangential component to get the flow, flux, or circulation. This is the second step. So in order to get that vector field down onto the path, we use dot product. And that's what we're going to do right now. Again, this step was not required for scalar fields, but it is required for vector fields. So we look again at the Riemann sum that we would expect. We're going to have to go F composed with R, we just did that in order to find the function in terms of parameterization. We're going to dot it with the tangent. This is that tangent vector, the t, from the first or second chapter of this class. And we take the dot product of it, and then we multiply by the little segment delta s. And we'll do the same for this segment as we did for the scalars. Okay, what is a unit tangent? The unit tangent is the first derivative, the derivative of r with respect to t divided by its magnitude. It is a unit vector in the direction of the first derivative of the parameterization. So we can substitute for t, and we end up with this. So that's our first substitution. Now we do the same thing with delta s. Delta s, again, the way I use it is it's the difference between the endpoints. It's a straight line distance between the two endpoints in r along the path. The difference quotient in the limit gives the first derivative, so I'm going to rearrange and say that delta s equals the first derivative, magnitude of the first derivative, times delta t, and substitute that. Here's the result of that substitution. We have f composed with r, then we have it dotted onto the tangent, which gives me r dot, the unit vector in terms of the parameterization, that's that tangent vector, multiplied by the magnitude of r dot times delta t, and that came from ds. Let me point those out again with the pencil here. Maybe if I make it not so wide, it will work better. Okay, so what we have, I'm going to write this bigger. We have f composed with r. We already had to do that both times, doesn't matter. Then we have a dot product with the tangent. That's to find that parallel component, and we replace that with r dot over its magnitude, the unit vector in the tangential direction. Then we're multiplying by the little segment ds to complete our Riemann integration, and ds is, let me write here, ds is equal to the magnitude of r dot times delta t, and that's why that appears here. Now obviously you can cancel those two, and we end up with, this is the result for the circulation. That would be the vector field, the component of the vector field as it flows around a surface. F composed with the parameterization, dotted with the first derivative, or the derivative rather, since it's only of t, the time derivative of the parameterization times delta t, and in the limit, this is a circulation along that path. And the endpoints are in t, because we're using the parameterization. Now we're going to do the same thing, but now we want the normal component because we're looking for flux. So the tangential component doesn't really cross a boundary, it just kind of lies on the boundary. The normal component actually crosses it, and that's why we're looking for that projection. And we want the outward normal so that we have some kind of consistency in our signs. Let's look just at the flux crossing this circle denoted by C in the xy plane. Right. We want the normal to it. What is a normal? The normal is the tangent cross, well, the binormal, but the binormal is k, right? Because it just points out of the plane. Right? So cross product of that gives me the outward normal. Now if you do it the other way, k cross t, you're going to get the inward normal and your signs will be wrong. So the normal is t cross k. We know what t is. So we'll start here. We want to dot it with that normal. We know the normal is t cross k. We know t is r dot over the magnitude of r dot, the unit vector in the tangential direction. So making those substitutions, we get this much. Delta s, we use the same substitution that we did before. Okay, and the substitution is delta s equals the magnitude of r dot delta t, and then we take the limit. So this is what I said at the end of the last slide. So we substitute that, And you can see here this is a cross product, and the these terms can get canceled, and you're left with r dot cross k, which you can actually write as a normal. It is a normal, but it is not necessarily a unit normal, but that's okay. And that is the expression for the flux across that surface.